I'm arm wrestling with this. There we go. Ooh, that's too much. Normally you think you can just reduce the window, you just drag the mouse. Here it's like you have to arm wrestle it. I'll need to start from beginning with that. Right. Share. Okay. All right. Okay. I want to kind of backtrack a little bit on the first thing I want to do today, and then we'll get back to computing the arc length for parametric curves. So here's something where we want to find the points on a curve where, and we've seen one problem like this before, where the tangent line is horizontal and where it is vertical. Okay, and the curve that we're given is this. It's x is equal to 3 plus the cosine of t, y is equal to 3 minus the sine of t. So this is a parametric equation, set of equations. It's a parametric curve. So we know this formula, dy dx, which is the derivative, is equal to this formula, dy dt over dx dt. It's basically like we divide the top and bottom by dt. So we need to compute these two derivatives here. So dy dt is equal to what? The derivative of the minus sine, so that's the minus cosine of t. So the top is minus cosine of t. The bottom, the derivative of dx dt is the derivative of the cosine, which is the negative sine. All right. So here's our derivative. So certainly I can cancel out minus signs, and it's cosine of t over the sine of t. All right. So to find out where this thing is, the tangent line is horizontal, that's, of course, where the derivative dy dx is equal to 0. And in this case, we need to look at the numerator. Okay, look at numerator. So the numerator is cosine of t, and we set that equal to 0. Okay, so then we have to think about what are some of the values of t that will give us a 0 for the cosine. Well, certainly one value is pi over 2, 90 degrees. And let's also add a second value here. Also, if we go around another 180 degrees, 3 pi over 2 also gives us a 0 for the cosine, all right? Okay, and then, so those are two values of t that'll give us a tangent line of 0. Notice that in either one of these, the denominator, which is sine of t, will not be 0. Then that's good. Denominator will not be 0. Okay. So basically, let's figure out, okay, t equals to pi over 2, all right? Let's plug this into our differential equations here. So that's x equals 3 plus cosine of pi over 2, which of course is 3 plus 0, so that's a 3. Our y value is going to be 3 minus the sine of pi over 2, and sine of pi over 2 is 1, so that's going to be 3 minus 1. Oops, how about 3 minus 1? So our y value is 2. So we have one point, 3 comma 2, in which the tangent line is going to be horizontal. However, if we also work with the other value of t equal to 3 pi over 2, we will get another ordered pair. The x value is going to stay the same. 3 plus the cosine of 3 pi over 2, that's still just going to be 3 plus 0, so that's just going to be 0. The y value is going to change, though. Y is equal to 3 minus the sine of t, so that's 3 minus the sine of 3 pi over 2. Okay, so what is the value then of the sine of 3 pi over 2? Negative 1, right. And you guys, I'm sure you remember, I mean, just because this whole section is kind of heavy on trig. All right, so Cassandra's going, yes, I'm so relieved, finally. Okay, we just know with this unit circle, we just look at these coordinates here, x and y coordinates, and 0, 0, minus 1, that the x coordinates along the unit circle will give us the cosine value, right? And the y values give us the sine value. So this is 0 degrees, this is pi over 2, this is pi, this is 3 pi over 2. So just an easy little diagram to reinforce that the sine of 3 pi over 2 is negative 1. So this is going to be 3 minus a negative 1, so I'm going to have a y value of 4. So my other ordered pair then is going to be 3 comma 4, where the tangent line is horizontal. Okay, now let's look at the other part of it. Where is it vertical? Well, it's going to be vertical where the denominator of our derivative is 0. Where the denominator of dy dx equals 0. So our denominator we had obtained was sine of t. So we set sine of t equal to 0 and figure out a couple of points where that occurs at. Well, one point is at 0 degrees, right? 0 degrees. And what's another point where the sine is going to then go back to be 0? Pi, right. Okay. So let's see what we get here then. And notice that at both of these points, our numerator, note the numerator here, which involves cosine, does not equal 0. So we don't have a 0 divided by 0 kind of thing. All right. So let's then fill in these. So here we're going to have, let's look at t equal, or angle t equals 0. Now x then is going to be equal to, it's 3 plus the cosine of t. So it's going to be 3 plus the cosine of 0, Cosine of 0 is 1, so that's 3 plus 1 is 4. Okay. And our y value then for t equals 0, well, y is 3 minus the sine of t. That's going to be 3 minus 0, so our y value is 3. So this ordered pair, 4, 3, is a place where our tangent line will be vertical. Okay. All right. And then let's look, though, we're going to get another, just like before, we're going to get another ordered pair here with pi for the t value. So here, x then is going to 3 plus the cosine of pi. Now, the cosine of pi is negative 1, right? So that's going to be 3 minus 1. So our x value here is 2, and our y value is going to stay the same. 3 minus the sine of pi is 3 minus 0, so our y value stays at 3. But we do get a second ordered pair, 2, 3, where the tangent line is a vertical line. Okay. So you'll see something like this in homework, so I just wanted to emphasize again. Any question on just that example? All right. Let's go back then to arc length. Let me start a new sheet of paper here. Imputing the arc length. And so let me write down again the formula when we have the parametric equation. L being the arc length is going to be the integral from A to B of the square root of dx dt in parentheses squared plus dy dt in parentheses squared dt. And that's where t, our parameter, say, is going from the number A to the number B. So that's the formula for arc length. Let me put an asterisk by that again. That's something you'll be expected to remember for these parametric curves. All right, so let's do we did a very simple example the last time. Let's do a little bit trickier one. So here, find the length of the curve. X is equal to 1 plus 3t squared. Y is equal to 4 plus 2t cubed. And our parameter t is going from 0 to 1. Okay. So we want to figure out, first of all, we have to figure out dx dt and dy dt. So let's do that. dx dt here is just going to be 3 times 2, 6t. Dy dt is going to be 6t squared. All right. Okay. So therefore, we have to square these. So dx dt squared is going to be 36t squared, and dy dt squared is going to be, let's see, 36t to the 4th power. Okay. All right, so let's get our integral going here. So it's going to be the integral from 0 to 1, okay, of the square root of 36t squared plus 36t to the 4th dt. And at first glance, you might think that this, well, it's going to be interesting getting this antiderivative. It actually involves a little bit of a trick that we sort of learned back then when we were evaluating antiderivatives. So, what do you think the first thing is I want to do with this antiderivative, with that radical?
You pull out a 36t squared out of
Yeah, I can pull out a 36 from both terms, and a t squared is common to both terms also. So basically, when I pull out a 36 out of the square root, I'm going to get a 6 on the outside. When I pull out a t squared, I'm going to get a t. Notice our t values here are positive, between 0 and 1. So when I pull it out, I'm just going to have a positive t. And then what I have left inside then, I'm just going to have a 1 left with the first term because I pulled out the full 36t squared. And with the second term, I have a t squared left over. All right. Okay. Now, this one, okay, how would we then, this one actually doesn't involve much of a trick, really. How are we going to evaluate this antiderivative here? U substitution, and what would be the u value then? Yeah. Have the u just be equal to 1, because notice we have a t on the outside. So let u equal to 1 plus t squared, and so the du is just going to be 2t dt, all right? Now we look up at our integral and we have a 6t dt, so one thing I could do right here is just multiply both sides of this by 3 and get the identity or equation that 3 du is equal to the 6t dt, all right? So anyway, so let's, now, one thing we need to do here, when we're doing u substitutions, unless we go back to our t variable, I need to change the limits of integration, all right? So I'm going to do that. When t is equal to 0 here, my u is equal to 1 plus 0, so it's equal to 1. When my u is equal to 1, then when my t is equal to 1, my u is then going to be 1 plus 1 squared. My u is going to be equal to 2. All right. So therefore, let's rewrite this thing now using our substitution. So now instead of 0 to 1, I'm going to first have my limits be 1 to 2. 6t dt up here I can replace with 3 times du. And then the radical gets replaced with u, the square root of u, or I could write it as u to the 1/2 power. And now this is an easy antiderivative to get. 3 times u to the 3/2 power. Now we divide by 3/2, but that's the same as multiplying by the reciprocal, 2 over 3. So I'm just going to do that right off the bat, times 2 over 3, all right? And then we put our bracket and we evaluate from 1 to 2, all right? So let's see, the 3's actually will cancel out here in the antiderivative. So we're going to have 2 times 2 to the 3/2 power minus 2 times 1 to the 3/2 power, which of course is just equal to 1. And, or I could write it, I could take out a 2 that's common to both of the terms and write it as 2 to the 3/2 power minus a 1, like that. Now, if this were a problem that you could say, look at the solutions at the back of the book, they would write 2 to the 3/2 power as 2 times radical 2. Okay, so that would be how the answer would be posed in the back. I'm fine with just keeping it as 2 to the 3/2 power, though. That's not a problem with me. So this is our answer right here for the arc length then. Let's see. All right, okay, let's move on then. That's the example I wanted to show on, another example on arc length. And this is more realistic as far as what you might see on a test, this kind of one that we just did. The next thing then we're going to look at, we're going to go from arc length to surface area, where we revolve the curve around an axis. Okay. All right. So this is now computing surface area. Where we're revolving a curve around either the x-axis or the y-axis. So I'll just say revolving a curve around an axis. And let's recall from that handout that the formula here. If we're rotating it about the x-axis, if rotating around x-axis, the general formula is this: integral 2 pi y times ds. All right. Now, if we're rotating it about the y-axis, if rotating around the y-axis, the general formula is 2 pi x ds, like that. Okay. Now, in this case, where we're talking about parametric curves, this ds here, that ds is equal to the square root of the dx dt squared plus dy dt squared, all under the radical dt that we had just used with the calculating the arc length. All right. So what we have here then is the form. This is what we get then for rotating around the x-axis. We have 2 pi y times the square root of dx dt squared plus dy dt squared dt, or if we're rotating that around the y-axis, it's 2 pi x times the square root of dx dt squared plus dy dt squared dt. All right. One of those two formulas. Yeah.
There's that one, and then what's the difference between the 1 plus the dy?
Okay, that is when we're working with a regular curve. Notice when we were working those, so the question is, what is the difference? Where's that? I think I've got that handout hanging around here somewhere. I think. Yeah. This handout here that you had gotten a while back. This is for where our curve is either y equals a function of x or x equals a function of y. This does not involve parameters at all. So this handout here, if you want to make a note onto it, is where we don't have any parameters. It's just what we would call just a regular function, a regular curve without the parameters. Okay, so I'm going to say no parameters here. All right, and those are the formulas then. Does that help? Okay. So back to these, I think I need to put, again, a remembrance, an asterisk there by those. That's something you're going to want to be able to recall. Okay, so let's do an example here with this. And this first example, it first looks like it's getting really, really horrible, but then it just simplifies. So, and you've seen that in homework where things initially look pretty awful, but you've seen that where things can then get simplified. So here's the example of find the area obtained by rotating x equal 2 cosine to the third power times theta, y equals 2 sine third power theta about the x-axis. And here theta is ranging from 0 to 90 degrees, or pi over 2. Now the first thing I want to say about this example is this, that all we're doing right here is replacing the variable t with the variable theta. Okay, so that's all we're doing. We just are calling our parameter by a different name. We're using theta. So notice t is being replaced by theta. Otherwise, everything is going to work the same. So what we have to get this, first of all, we need to get the dx d theta and the dy d theta, okay, because we're going to have to be squaring those. So let's find dx d theta. So here's our x, so we're going to need to use the chain rule with this. We're going to need to bring our exponent of 3 down, so 3 times 2 is 6. Then we have a cosine squared, and then with the chain rule, we have to then multiply by the derivative of the cosine, which is the negative sign. All right, so this is chain rule. And let me just rewrite this. So I put the negative out front. So we have minus 6 cosine squared of theta, sine of theta. That's our dx. And now let's get the dy, d theta. Again, we're going to use the chain rule, bring down our 3. 3 times 2 is 6. And then it's going to be sine squared of theta. And then chain rule derivative of the sine is the cosine times the cosine of theta. All right. Okay. And then we're going to be squaring those. So remember our general formula here. Now we're rotating this about the x-axis. So let me just write down what our general formula is. It's going to be 2 pi y ds, because we're rotating about the x-axis. All right. So, first of all, our limits of integration are going to be 0 and pi over 2. Let's write the 2 pi down. Now let's write down what y is, and y is equal to 2 times sine cubed of theta. And then let's get a big radical here. And we first have to multiply dx, d theta. We have to square it. So here's what we're squaring right here. So we're going to get a positive 36. We're going to get a cosine to the 4th of theta and sine squared of theta. Going to square everything there. And then we have to then square the dy d theta. So that again, 6 times 6, we get another 36. Sine, we square the sine squared, we get a sine to the 4th. And then cosine squared of theta. And that's all under the radical. All right. So let's look at this. And let's see what we can do here. Okay. Well, what can we do here with this radical? Yeah.
Can take out 36 codes and first.
Yeah, okay, so we can take out a 36. We've got a cosine squared that's common to both terms, and we have a sine squared that's common to both terms. All right. So let's take out, I'll put that in quotes, 36 cosine squared theta, sine squared theta from under the radical. Okay, let's see what we get here. 0 to pi over 2. Why don't I multiply this 2 and 2 together? 4 pi sine cubed of theta, so I'm just rewriting it. Okay, so we're going to take out 36, so that's going to give us a 6. We're going to take out cosine squared, that's going to give us a cosine. Sine squared, that's going to give us a sine. Notice that between 0 and pi over 2, both cosine and sine are positive. So I don't have to worry about any plus or minus there. It's going to be a positive result. Then let's put what's still left under the radical. Well, I think in the first term, all I'm going to have left is the cosine squared, right? And in the second term, all I'm going to have left is a sine squared. Oh, that's interesting. Okay. So, what's that radical now become? 1. Cosine squared plus sine squared is 1. So this whole thing here just equals a nice 1. All right. That's where I said it simplifies to where it's reasonable. Okay, so let's rewrite this thing now. 0 to pi over 2. Let's combine some numbers. 6 times 4 is 24 pi. And then we have a sine cubed and a sine, so that's going to be a sine to the 4th theta. And then we have a cosine theta, and then we have our d theta. All right. Okay. So now what can we do here with this to get this answer?
The u substitution.
Okay, and what's going to be our u?
Sine.
Sine? Oh, yes, exactly. Sorry. Yeah, u is going to be sine of theta. All right. So therefore, our du then is going to be cosine of theta. Derivative of sine is cosine. All right. So, and now I also then want to, while I'm at it, let me change the limits of integration. Now, if you don't change the limits of integration, you need to get everything back in terms of theta in your antiderivative. I think it's easier to change the limits of integration and be done with it. So when theta is equal to 0, well, the sine of 0 is just 0. So u is equal to 0. Now when theta is equal to pi over 2, u is the sine of pi over 2, so u is equal to 1. All right. So our limits of integration then are going to be from 0 to 1. And let's see, let's copy this stuff here. We have a 24 pi. Now sine to the 4th is going to be replaced by u to the 4th. And the cosine d theta is going to be replaced by du. All right. So now that becomes a nice integral to get. So that's going to be 24 pi times u to the 5 divided by 5, integrated from 0 to 1. Okay? And then that's going to be 24 pi times 1 over 5, so I could just write it as 24 pi over 5, and that'll be, of course, minus 0. So this right here would be our surface area then. Okay? Question about that? Let's do one more before we take a break, and this is the one that involves a little bit of trickiness with getting the antiderivative. So now we're finding the surface area generated by rotating, let's see, x equal to 3t squared, y equal to 2t to the 3rd, and this is where t goes from 0 to 5, and this time we're rotating it around the y-axis. Okay. So our general formula then is going to be 2 pi x ds, because we're rotating around the y. All right, so let's rewrite this then. Our limits are going to be from 0 to 5, 2 times pi. Let's write in the x here. That's 3 times t, 3t squared for the x. Oh, I better, you know what, before I do anything further, I think I need to get the dx dt and the dy dt, huh? So dx dt is going to be 3 times 2, 6t. And dy dt is going to be 2 times 3, 6t squared. So when I square those, I'm going to get 36t squared. And when I square the dy dt, I get also 36. but now I get t to the fourth power, okay? All right. So now let's do the radical here. So this first term is going to be under the radical 36t squared, and the second term is going to be plus 36t to the fourth dt. All right. So we got very much similar kind of thing that we had in the last example. We can move some stuff out of from under the radical. Certainly the 36 and a t squared is common to both terms. So let's move 36t squared out from the radical. So what are we going to get? 0 to 5. Let's multiply my numbers together. 2 times 3 is 6 pi t squared. And so the 36 is going to give me a 6. The t squared is going to give me a t. And then I still have under the radical, what do I have? The first term is just going to be a 1, right? Because I moved that whole part out. And the second one is just going to be a t squared. dt. All right. Now, what we have here then, notice what we have. We have t cubed, and we have 1 plus t squared under the radical. Ugh. All right. So here involves some trickiness here. All right. One of the tricks that was mentioned there in that general strategy for doing antiderivatives was to sometimes it's helpful, if all else fails, is to see if putting u equal to what you have under the radical, see if that helps. All right. So I'm going to try that. Let u equal 1 plus t squared. Okay. All right, so what happens here with this? First of all, one thing that I get here from this, well, let me put the du down. So du then is going to be what? 2t dt, like that. All right, but if you look up here, it might be real helpful here to kind of rewrite that u equation as noticing that t squared, if I subtract 1 from both sides, t squared is also equal to u minus 1. Okay? And that's going to be real helpful, believe it or not. I guess you know what, while we're at it, let's look at changing the limits of integration before we go any further with this. Okay, so when t is equal to 0, then u is going to be 1 plus 0, so u is going to be equal to 1. And when, let's see, the top one is 5. When t is equal to 5, u is 1 plus t squared, so it's going to be 1 plus 25, so it's going to be 26. Okay, so let's get that adjusted. So then our new integral then is what? 1, going from 1 to 26. All right. Now, we have 6 pi. Now, we have t cubed. We need to save one of those t's for the du, right? In fact, actually, keeping it written like this would even be more helpful to you. I know I have to save a t for the du, but what I have left over is a t squared. But I can rewrite t squared as u minus 1. So therefore, I'm going to put, for t squared here, I'm going to put in parentheses u minus 1. And then we're going to have, let's see, so that's the t squared. We still have a 6 here. All right. Why don't I do this? I've noticed what I've got here is I've got a 6 dt here. What could I do here with this du equation? I could multiply it by something just to make life easier. By 3, yeah. 3 du is the same as 6t dt. So going back here then, that 6t then can be replaced by a 3, and we have a du out there to the right. And so the only thing I have left then is the square root of 1 plus t squared, and that's the square root of u. All right. Okay, let me kind of straighten this thing up then. But are we okay so far kind of following? It's a little bit of a tricky substitution, but it'll work. All right. 1 to 26, let's see, 3 times 6 is 18 pi. And then why don't I just be distributing the u minus 1 and the square root of u? So that's going to give me u to what power? U times square root of u is going to give me u to what power? Yeah, 3/2. And then minus 1 times the square root of u, that's going to be minus 1 times u to the 1/2 power. Okay. All right. So with this substitution, we've been able to get it now into a manageable antiderivative. We can just do that now. Okay, so let's see. We have 18 pi, and then this is going to be what? Antiderivative of this is going to be, what are we going to get? 2/5 u to the 5/2 power. Again, you add 1, you get 5/2, and when you divide by 5/2, it's the same as multiplying by 2/5, and then minus 2/3 u to the 3/2 power. And then that's all being evaluated from 1 to 26. So we're going to get some kind of like ugly looking answer, but at least it's correct, all right? Okay, so let's figure this thing out here. We're going to end up with having to deal with a couple of fractions when at the end. So the 18 pi I'm just going to keep out on the outside. So here we plug in the 26, so it's 25 times 26 to the 5/2 power. And then I have to plug in the 26 again, minus 2/3 times 26 to the 3/2 power. All right. And then I have to plug in the 1. So be careful with your minus signs, because now I have to subtract. So that's going to be minus 2/5 here when I plug in the 1. But here I've got a double negative, so I'm going to have plus 2/3. And I've got that. Okay. The only other thing I would be interested in with this is just combining these two fractions together. So what would that give us? I just like to do the little cross-multiplying deal. Anybody want to be brave enough? 4/15, right? Okay. 2 times 5 is 10, minus 3 times 2, that's 10 minus 6 is 4, and then you multiply the denominators, so 4/15. So anyway, I certainly am not interested in doing any further simplification with that. I think the book does further simplification. I'm not worried about it. That's fine, okay, as an answer. All right. Any question then on the second example? A little bit tricky with the substitution, but the main thing here, of course, is just to recognize, going back here, just recognizing initially these two basic formulas here, and you're going to be in pretty good shape to go from there. If rotating around the x-axis, it's 2 pi y ds. If rotating around the y-axis, it's 2 pi x ds, right? And I don't think that is too hard to remember with that. All right, Now, on to, where is it? Okay, did it walk away from me like things do? Okay, here we have it. Now we're going to talk about, we're on to the next section, and this is another way to represent curves, and it's called polar coordinates, right? Which is something you should have been introduced to in trigonometry. But I'm going to go through a little bit of, I'm going to do a 5-minute trig course. Okay, trigonometry in 5 minutes. Okay, first of all, what I want you guys to remember are, and so when I mean remember, you know what I mean, trig formulas. These trig formulas. The sine of 2 alpha is equal to 2 times the sine of alpha cosine of alpha. The cosine of 2 alpha is cosine squared of alpha minus sine squared of alpha. Then the sine squared of alpha is 1/2 1 minus the cosine of 2 alpha. And then finally, the cosine squared of alpha is 1/2 times 1 plus the cosine of 2 alpha. All right. Because you'll need those formulas to simplify things for antiderivatives. Okay. So we want to make sure we remember those trig formulas. The next thing, just a little recap here, the 4 quadrants. We start, number 1 is in the upper right. We go counterclockwise. So we have the 4 quadrants. And does anybody remember a little 4-word stupid statement to help you remember what's plus or minus in each one of these 4 quadrants? What? All students take calculus, A, S, T, C. Okay? When I taught trig, I wanted to give an affirmation to my trig class, so I had it as a smart trig class. All right? So anyway, what do these mean? This is where the sine is positive. This is all of them are positive. This is where the tangent's positive and the cosine's positive. All right. Okay. The next thing then is kind of an abbreviated little unit circle. Ooh, almost looks like a circle. All right. 1, 0. Well, we had just done this other thing, 0, 1, minus 1, 0, 0, minus 1. That's what we just did a few minutes ago. But here, for the unit circle here, we've got a 30-degree angle, a 45-degree angle, and a 60-degree angle there in that first quadrant. And so the coordinates are going to be your sine and your cosine. So we know that this one starts out as square root of 3 over 2, and then 1/2. This one, oh, what the heck, why did I do that? Square root of 2 over 2, square root of 2 over 2, and that's for this is for 45 degrees, this is for 30 degrees, which is pi over 6, pi over 4, and then for 60 degrees, it's going to be, 1/2 square root of 3 over 2, all right, and that's for pi over 3. Okay, of course, you have your special triangles to help you with remembering that, right? The 30, 60, 90 triangle and the 45, 45, 90 triangle, all right? The last thing then in this 5-minute trig course is this. It has to do with reference angles. Does anybody remember the term reference angles? That's to help you figure out the sine and cosine of things that aren't in that first nice quadrant, all right? So if we had something like, and I can tell Cassandra's getting ready to give me the answer. So if we had this angle here, which is, let's say this is 2/3 pi, all right? And let's say we want to figure out the sine of 2/3 pi and maybe the cosine of 2/3 pi, all right? Let's put in my ASTC for good measure, all right? So for the sine for 2/3 pi, unless you just have it all memorized in your head, which I don't, what is the reference angle for that? Or do we remember how the reference angle is even calculated? Yes. Do you know why? Yeah, it's this angle, yes, exactly. It's pi over 3. It's that angle right there when you drop it down to the x-axis that you get. So the reference angle, in this case, is equal to pi over 3. Pi minus 2/3 pi. All right. So therefore, the sine of 2/3 pi is going to, first of all, it's going to be a positive number because it's an s in there. And then we just look at what's the sine of pi over 3. Of course, so therefore and just to remember, we do our little, if need be, just draw your little special triangle there. And this is 60 degrees, this is 30 degrees, which means pi over 6, pi over 3. And this is going to be a 1, this is square root of 3, and that's a 2. So the sine of pi over 3 is going to be opposite over hypotenuse, so that's square root of 3 over 2. And we know it's going to be, and square root of 3 over 2, so up here, it's also going to be a positive number, so it's the square root of 3 over 2. What about the cosine of 2/3 pi? Is that going to, first of all, is that going to be a positive or a negative value? It's going to be a negative value, because there's no c there. And so what's the cosine of the reference angle? The cosine of 60 degrees is adjacent over hypotenuse is 1/2. So it's going to be minus 1/2, all right? And you can do that then with, say, 5 pi over 6, 7 pi over 6, all those things you can, for me, whenever I taught trig, and of course when you teach it, you have to do it also, I would just be drawing things all the time, you know, just on scratch paper, because I tend to be visual, and if I don't see it, sometimes I'm not smart enough in my own head sometimes to just visualize it. I don't trust myself, let's put it that way. And also one last thing, how do we measure angles? We know that we measure angles from right here, all right? If I'm going in this direction here, measuring this way, is my angle negative or positive? If positive angles go, or now if I measure in this direction, however, my angles are measured negatively, all right? All right. So, you know, there you have it, all right? Trigonometry in a nutshell. Okay, so let's go then to this polar coordinate stuff. Now what we're going to do is, polar coordinates give us a different way to designate a point on the plane. Oh, you know what? I'm going to write this and then we're going to take a break. Different ways to designate a point on the plane. And let's take a 5-minute break then on that note. What happened? How do you miss stuff from me?
I think that it's only one question, so I do sections at a time.
Yeah.
So
All right. Where is it again? Oh, there it is. That looks, yeah, that, I remember that's the, okay. So the, oh, okay.
On Monday.
all right. I think we'll get started here. Okay. So the way is different way to designate a point on the plane. So let's just look at x, y there. And let's just put a point up here. Now, the Cartesian coordinates, we just measure the distance from the axes, and that tells us what the coordinates are. Here we have two ways of doing it. We, first of all, it's designated by the distance absolute value of r it has from 0, 0. And actually, there's a special name for that 0, 0, and it's called the pole. Okay. So therefore, we can just draw a straight line here, and this distance here, absolute value of r, whatever that distance is. There's a reason I have the absolute value there, by the way, and I'll say that in a minute. But the other thing then is, okay, distance, well, there's a whole lot of points that have that distance r from the pole. Also, we have the angle theta that it makes with the positive x-axis. That it makes with the positive x-axis. So here we have an angle theta that is made with that positive x-axis. Now, another bit of terminology here, the positive x-axis is called the polar axis. So on this graph here, that positive x-axis, that's our polar axis, all right? And then this 0, 0 here is the pole. So this point way out here, it has the two coordinates, r and the theta. Okay. Now these are called the polar coordinates then. R, theta are the polar coordinates. Okay. Now the thing is, let's first of all remember that if theta is positive, then the angle is measured counterclockwise from the polar axis. So the angle theta is positive when it's measured counterclockwise from the polar axis, or the positive x-axis. And then it's negative when measured clockwise. When measured clockwise. All right. Okay. Then this r. This r here doesn't have to be a positive number. If it is a positive number, then the point lies in the same quadrant as our angle. So if r is bigger than 0, then the point lies in the same quadrant as the angle. And we'll go through a couple of examples in just a second. In the same quadrant as the angle theta. However, if the r happens to be a negative number, then the point lies in the opposite quadrant from the angle theta. If r is a negative number, then the point lies in the opposite quadrant as the angle theta. As the angle theta. All right. Okay. So let's look at some examples here with this. This, by the way, is a polar graph. You probably have seen these before. So basically, we have these concentric circles that represent different values of r, the distance from the pole, and then we have these lines emanating out from it which represent different angles as we go around the circle. Okay. By the way, this graph is posted on Gateway, as well as I've got a couple of variations of this. I've got another variation where, to save a little bit of paper, I have 2 on 1. Okay, and then a third variation to save even more paper. I have one that is 6 on 1 on Gateway. All right. Oh, you know what? On Blackboard. Also calls it Gateway. Blackboard. Sorry. Blackboard is what I mean. Okay. So there's plenty of graph paper out there. It's just the cost of printing it out. All right. So let's look at some examples here. Let's first of all plot. Let's see. Plot in polar coordinates 1, 5 pi over 4. All right, so let's see. This is 0.5. This is 1 right here going out. But then we have to find 5 pi over 4. So we see that it goes around, and then we go down to in the third quadrant here, 5 pi over 4. All right? So we have to be on the 1, go around to 5 pi over 4. So right there, that dot there is that point, okay? Let's look at plotting 2, minus, I'm sorry, how about 2, 3 pi. 2, 3 pi. Okay, so for 2, we need to make, let's see, we have, this is 1, this is 1.5, so this is 2 going out here. And now we got to go to 3 pi. So where is 3 pi going to be here? It's going to be at pi, because we can always, anytime we can always go around an extra 2 pi, and all we're doing is revolving around the whole circle. So right here, this would be, so let's go around, blah, blah. And here we have pi, and that's exactly where it would be right there. Okay? All right. Now let's look at a negative angle. Let's look at plotting 2, minus 2 pi over 3, or minus 2/3 pi. So again, we look at our, we get to 2, 1/2, 1, 1.5, 2. So here's 2 out. And then, let's see, now we're measuring the angle negatively, so we have to go clockwise. So, minus 2/3 pi. Now, I don't see a minus 2/3 pi on here. Where's that going to be? Yeah, it's going to be a 4 pi over 3. Because basically, as we go around here, this is minus, that's minus pi over 2, and then we have to go 2/3 of the way to the pi. So if we go to 5 pi over, 4 pi over 3, we end up at 2/3 of the way, right there. Okay. All right. Last one I want to look at here, this is where we have a negative r value. Negative 3 for r, and our theta value is 3/4 pi. Okay. So with r being a negative 3, it is going to lie 3 units away from the pole. So let's see. 3 is going to be here, this circle right here. All right. Now, let's figure out, okay, where is 3/4 pi? So we go around, we see 3/4 pi is up here, so we go around. Here's 3/4 pi. But this point here, this is positive 3, 3/4 pi. To get to negative 3, 3/4 pi, I take this point here, trace it through the pole, go all the way on the other side of the pole to where I'm again at the distance 3. So I have to go to the opposite quadrant of my angle. My angle 3/4 pi is in the second quadrant. But since it's a negative 3 for the r, I have to trace it across, and let's see, let's make sure this is right. This is, whoops, that is 3, and that is, Right. Right there. Okay. So you have to go to the opposite quadrant if r is negative. Okay. And hopefully this is ringing a bell for you guys from trigonometry. One other point I want to make is that any single point on this polar graph can be represented really in infinite number of ways. Let's look at a 1 comma 5 pi over 4. So let's try to find that. Okay, this is 1. And then 5/4 pi is down here, 1 1/4 pi. Oh, okay, well we already did that one, didn't we? So here it is, all right. But I can represent that as 1 comma, let's see, if I go in the negative direction, that's going to be what? Negative 3/4 pi if I go the other direction. Or I could go around another whole 2 pi, and I could have it be 5 pi over 4 plus 2 pi, adding on to that, and that'll give me 13 pi over 4, just doing another revolution. So I have that designation. Okay. And and here's another way I could do it. Here's 5 pi over 4. I could go to the other side of the angle to the other side of that, which is pi over 4, and put my r as -1. That's another way that I can represent that point. So there's an infinite number of ways that a single point can be designated, all right? Okay. Okay, the next thing then, again, hopefully this should continue to be some kind of review for you guys, is what's the connection between the regular Cartesian coordinates that we're used to and the polar coordinates. So connection between polar coordinates and what are called Cartesian coordinates. And Cartesian coordinates. All right. Okay. All right, let's draw a picture again. X and Y. Let's put a point up here. All right. Now, in Cartesian coordinates, we just would represent this as x comma y. All right. In polar coordinates, though, let's see, we have a distance here of r and an angle here of theta. So in polar coordinates, this would be represented as r comma theta. Let me drop down a dotted line here. The length of that vertical line is the length of the y value. And then the length here is an x, the length of the value of the x value. So now we have a right triangle here. All right, so we have an angle. So the cosine of that angle is going to be equal to the adjacent over the hypotenuse. So cosine of theta is equal to x over the r. And the sine of that angle, sine of theta, is the opposite over the hypotenuse. That's going to be y over r. And then if I multiply both sides of these equations by the denominator r, I get that r times cosine of theta is the same as x, and r times the sine of theta is the same as y. So I want to put with asterisks here. You need to know these relationships here, all right? So basically then, if we know an r value and a theta value, in other words, if we know the polar coordinates, we can plug those into these two formulas and get the x and the y. So, if we know polar coordinates of a point, we can determine the Cartesian coordinates, or we can find the Cartesian coordinates. The Cartesian coordinates. Okay, so let's do an example of that. Say that the point is 2 comma pi over 3. So this is our r, and this is our theta, all right? Okay, so therefore, that tells us that x is equal to r times the cosine of theta, right? So r is 2 times the cosine of pi over 3. That's 60 degrees, so the cosine is 1/2. So this is 2 times 1/2, so our x value there is a 1. Y is equal to r sine of theta, so that's going to be 2 times the sine of pi over 3. Sine of 60 degrees is the square root of 3 over 2. 2 times the square root of 3 over 2, which is equal to the square root of 3. So the xy then, for that polar point, is x is 1, y is the square root of 3. Okay? So we just plug the r and the theta into the formulas and we get the x and y. Now the thing is, we can also go in the other direction. If we know the Cartesian coordinates, the x and the y, we can then determine polar coordinates. So let's do that. So we can also go in the other direction. And so from Cartesian coordinates to the polar coordinates. All right. Let's draw another little picture here again. Here's our y and our x. And so now we're going from Cartesian to a polar. So let me draw a point there, and we'll call this just x comma y. All right? And let me drop down a vertical line to get a right triangle, and let me draw a diagonal line from the origin. Okay, so this length of this vertical line is our y value. The length of the horizontal line is the x value. And so using the Pythagorean theorem, the length of the diagonal line is the square root of x squared plus y squared. And of course, this is equal to our r, all right? So we have this, x squared plus y squared is equal to r squared. If I do the square root of both sides, I have r is equal to the square root of x squared plus y squared. Okay, so this is another relationship we need to remember then. Okay, so therefore, if we know the x and the y, we can find the r. Now, what about the theta? We also need to find that. Here, of course, right here, we can say that's our angle theta right there. So, in terms of the x and the y, notice that the tangent of our angle theta is the opposite over the adjacent, so the tangent of theta is equal to y over x. Okay? Now, one thing we have to be careful about is this. We have to make sure, caution, make sure that the theta that we come up with is in the same quadrant as the point that we're talking about. Is in the same quadrant. Actually, what I really should do here is I really should say the following. Be sure that the r comma theta that we are coming up with is in the same quadrant as our initial point, is in the same quadrant as our initial xy. Okay. All right. So this is a little bit trickier than the other way to figure this out. So let's start with an xy value and see if we can get an r theta. So we have an xy value equal to 1 comma minus 1. All right. And represent this point with polar coordinates. Represent this point with polar coordinates. All right. Okay, so that means we have to find an r, and we have to find a theta. Okay. Actually, the r isn't too bad, because r is just the square root of x squared plus y squared, right? So r is equal to the square root of 1 squared plus minus 1 squared, and that's just going to come up to be the square root of 2. That's not bad. Theta is something that can be a little bit tricky. All right. Now, remember, from up here, the tangent of theta is equal to y over x. So tan of theta is equal to y over x. Now, in this case, our y is negative 1, our x is 1, so that is equal to negative 1. So our tangent of theta is negative 1. Okay. What angle well, first of all, what angle has a tangent equal to positive 1? Pi over 4, 45 degrees, okay? So we can say kind of think out loud to ourselves, well, the tangent of pi over 4 is equal to a positive 1. So what angle then would give us a tangent equal to negative 1? Yeah, 7 pi over 4 would work. Okay. I was thinking of minus pi over 4, but 7 pi over 4 is fine. So let me just put it this way, because it can be more than one value here. So tangent of go 7 pi over 4, 1 3/4 pi, that is going to equal the negative 1. Remember again, a smart trig class, ASTC, in the fourth quadrant there, and in the second quadrant, the tangent is negative, all right? So 7 pi over 4 is in the fourth quadrant, and its tangent is minus 1. And then also, I could just have tangent going in the clockwise direction. The tangent of negative 4 is also equal to negative 1, all right? Okay, so here's one, before we get to our final answer here, but also, what's the tangent of 3/4 pi? What quadrant is 3/4 pi in? It's in the second quadrant. So it would have a negative tangent, right? So it would have a tangent with a reference angle of pi over 4. It does have a tangent of negative 1, all right? However, we have to make sure that our point is in the same quadrant as our initial xy. Well, what quadrant is 1 comma minus 1 in? It's in the fourth quadrant. So the r theta that we come up with has to be in the fourth quadrant, all right? Not in the second quadrant. So our answer here can be, we have a couple of answers right here. We know that the r is square root of 2 works. And for the theta, we can either have 7 pi over 4, that's certainly going to work, or we could have square root of 2 minus pi over 4, that can work also, all right? So you do have to watch out for where that quadrant, what quadrant you're in. All right. Okay, so this is our brief reintroduction into polar coordinates. Now what we're going to get into is what are called polar curves. I'm not sure today if we're going to get into the actual calculus of this. I don't think we are. That'll be on Friday. Okay, polar curves. Well, polar curves are represented using the variables r and theta. So, the graph of r equaling some function of the angle theta, what does this mean? If this consists of all points r comma theta that satisfy the equation. Okay. And so we can graph these. We can generate a little table and we can graph these. We can graph this using a table of some kind to generate the points. And another thing we can do is often we can convert this polar curve into an equation with x and y. We can convert into an equation with x and y. And of course, these are the Cartesian coordinates. Cartesian coordinates. All right. Let's just look at a couple of examples here today then. The first polar curve is just this. R is equal to 2. So what this means is this is all the points that has a distance of 2 from the center point. Okay? All points whose distance equals 2 from the pole. Okay, well that's going to be a circle, right? If we look at this thing, we count out 2, 1/2, 1, 1.5, and 2, and it's going to be everything around that circle there where r is equal to 2. Okay. What about then, say you were asked to find the corresponding Cartesian equation. Find the corresponding Cartesian. Now, Cartesian just means that we're talking about the x's and the y's. All right. Okay. Well, what do we know about r with respect to the x's and the y's? It's equal to the square root of x squared plus y squared, right? Recall, r is equal to the square root of x squared plus y squared. So all I have to do is plug that into our equation here, and I have the square root of x squared plus y squared is equal to 2. Or I could square both sides and come up with x squared plus y squared is equal to 4. All right. And as you know, then that is, of course, the equation of a circle centered around the origin 0, 0, and radius equaling 2. Okay. Any question on how I converted that thing to the Cartesian? using that identity, r equals square root of x squared plus y squared. Let's look at another one. Here we have theta is equal to pi over 3. So this is all the points, r comma theta, whose angle is pi over 3. Okay? So if we look here at a graph, here's pi over 3 right here, and it's everything that has that angle pi over 3. So we can go all the way up, all the way through this, and we can also go to the other side. The other side would represent the negative r, all right? Over here, this would be -1 comma pi over 3. So I can go all the way here to this other side. Okay, so that's the graph of that. And let's then find the corresponding Cartesian equation. Cartesian equation. Okay. So now we have a theta rather than an r. But what do we remember about the theta? The tangent of theta is equal to y over x. Recall. All right? So now all I need to do for the theta is plug in my pi over 3. So I have the tangent of pi over 3 is equal to y over x. Okay, so what's the tangent of 60 degrees? Square root of 3 over 1, square root of 3. So this is the square root of 3 is equal to y over x. So that's fine. That's certainly one answer, just like that. Or I could also multiply both sides by x and have y equals the square root of 3 over x. And of course, this is a straight line. And its slope is equal to the square root of 3, which is just what we had there when we drew the diagram. Okay. This next one we'll just kind of do half of, because I don't think we have time to graph it, but I just want to get it started. So here's another example. And here the curve is r equals 2 times the cosine of theta. And next time we'll graph it. But let's, for right now, let's just see if we can find the corresponding Cartesian equation. All right. Okay. Well, let's see here. Let's just throw down some things on the paper and see what we come up with here. We know that r is equal to, we know that x is equal to r cosine of theta, right? Okay. Okay, that's one thing we know. Notice what we have up here in our equation. We've got a cosine of theta in there. Why don't we, first of all, just take this thing that we know is an identity between x and r theta. Why don't we just divide both sides by r? And so let's do that. So that gives us x over r is the same as the cosine of theta. Okay? All right, well, let's do this then. So let's take what we have. We have r equals 2 cosine of theta. So I'm going to put that as r equals 2. Now, instead of the cosine of theta, then, I'm just going to put my new representation of it, which is x over r. Okay. Like that. Now, does anybody have an idea of where I can go from here? Yeah, if I multiply both sides by r, or cross multiply, I'm going to have, what I'm going to come up with is an r squared on that left-hand side. And r squared is equal to x squared plus y squared. And that'll do it. So let's multiply by r. So we have r squared is equal to 2 times x. And then recall, r squared is equal to x squared plus y squared. And now let's plug that in then. So we get x squared plus y squared is equal to 2 times x. All right, like that. Now actually, this is going to end up, this is fine for an answer, but it doesn't really tell us a whole lot about what this curve looks like unless we start really graphing it. First of all, does anybody have questions on just how I got to this, where I just had x's and y's? All right, let's get 0 on one side, so let's subtract 2x from both sides. So I get it, I'm just writing it now like this. And anybody have an idea what I'm going to come up with or what I can do next to kind of manipulate this thing? Yeah, I can complete the square of for the x's. Complete the square for the x's. So that gives me x squared minus 2x. So I divide the minus 2 by 2. That gives me a negative 1. And then I take the negative 1 and I square it. So that gives me a positive 1. That's what I have to add on. So plus 1 plus the y squared. And don't forget, you have to add whatever you're adding on to the left side, you got to add it on to the right side. So now what I have here is a perfect square, x minus 1 squared plus y squared is equal to 1. And that's a circle. This is a circle with center 1 for the x and 0 for the y. So it's a circle with center 1, 0. And what's the radius of the circle? 1. Radius 1. And actually just, and we'll do more detailed graphing the next time because I want to go through that process. But just with this, the circle radius 1 has center 1, 0. So here's 1, 0 right here. And so if it has a radius 1, it's going to be a circle like this in our x and y plane. Okay. So we'll continue with that the next time then.
Do you post the homework for 10.1 on Blackboard?
Oh, I didn't do that. I didn't do that yet.
I haven't looked on it.
Oh, 10.1. Oh, okay. You're really moving ahead, Will.
I just figured 9.3 was like Monday, so.
Yeah. Okay. Yeah. I'll get that posted.
Okay.
Well, you know what? Actually, I printed out hard copies this morning. So ask and you shall receive.
Right. Could I get the study guide for this next test a bit earlier?
The study guide a bit earlier. Okay, Kyle. Well, we can talk about that. Yeah. Don't overwhelm me too much with more than one thing. All right.
Yeah, that's all I really want.
Right, because what's going on? Are you going to be out? What's going on? You out? Why? Just you want to get started earlier?
When is your final?
Thanks.
I would not.
You want that?
All I know is that I have a final today.
Oh, it'll be recorded. Absolutely. You're talking about correcting, right?
Yeah.
Totally recorded.
Do we have off for Thanksgiving?
Not enough.
Wednesday, Friday.
Friday.
Just Friday.
And since we are officially here on Wednesday, I will also be here on Wednesday talking to whatever or whomever, but I'll be up here talking.
Well, it's not a Thanksgiving party.
Yeah, can we do that instead of
Bunch
learning?
Jenna, do you want to be in charge of refreshments then?
Okay.
I'll bring